And I know that doesn't spell out, there it is, Vesper, but they call it Vesper, like, anyway. And it has to do with understanding why molecules have different shapes. So you got carbon dioxide and water, for example. Just to give you an example. Here you got one carbon with two oxygens. Here you have one oxygen with two hydrogens. You think they have the same shape, but they don't. This one is polar, and the angle between the two hydrogen atoms, and my head is the oxygen atom, is 109 about, 109.5. Next with water, it's like 107 about. With carbon dioxide, it's 180 degrees. So Vesper theory helps you understand why that happens that way. And when you get that in your books, let me know, we can talk a little bit more about the details how to do that. Because it's a real simple little method once you understand that really helps explain a lot of things. So, carbon tends not to form polar molecules. That's why polar things dissolve in polar solvents, and non-polar solutes tend to dissolve in non-polar solvents. And water is non-polar. If that's carbon, it's organic, right? So, anyway. So, while we pray, go ahead and get started. We'll talk a little bit about what's coming up in the lab next week. Let me get my notes out. I got stuff to pass back to you guys. All right, let's pray. Father, we just pray that you will help us to understand as each one of these people or students are using different books, or many of them are using different books, so they're not all at the same place. And Lord, we pray as we do labs, and maybe there's parts of the labs that we haven't covered yet in our books and we don't understand as well. Pray and help me to make things more clear and each one of the students to get a better understanding of the concepts they're learning as a result of the labs. Thank you, Lord, in Jesus' name. Amen. Okay, let me see attendance. Who is not here? And that would be Gavin.
I don't think, based on what I've heard, I don't think he's going to come back for the rest of the semester.
Right.
That's a long time.
Because his sister, because we don't know when that's going to happen. I texted the other day and he said, yeah, I don't want to go back.
There it is. Okay. So you're having somebody help you to get caught up?
Yes, sir.
Okay. Let me know if you'd like to get some help, with tutoring to get caught up too. And some guys, if you want to get together sometimes as a group for tutoring, I guess you guys have been meeting at Panera Bread. Yeah. Just let me know if we can work that out. I'm also working with another organization called Huntington Center. They were started actually by the education department. So anyway, I'm doing tutoring for different science subjects. I actually have me tutoring first and second graders. Like, what am I doing here? That's not my prep. But okay. If you got your lab matters, why don't you turn to lab 3? And that lab that we're going to be doing next week is about the electroconductivity of different solutions. You're actually going to use, you have a little tester, but you're going to have all right. So you're going to put different solutions in here you're going to create. Then you're going to put this tester in there and you'll see how well it conducts electricity. Okay? It'll be the brightness of the light that shines. If it's not conducting electricity, you're not going to have any light shining. So it's kind of somewhat subjective. I mean, you're not doing an actual calculus where you can say this is 1.4 times better conductivity than that one. We won't be doing that, but you're getting an idea. So that's what this is about. Water conducts electricity a little bit because it has what's called polar molecules. Does anybody remember with the oxygen and the hydrogen? Let's say here's the oxygen, we'll say in the middle here. And then we have hydrogen atoms. Which part of this molecule is negative, which part is positive?
The oxygen's positive and the hydrogen's negative.
So which one's positive?
The oxygen, isn't it?
Because it's red.
It's actually negative, and then the hydrogen is
Oh.
positive. So we know why that happens? It has a chart like that.
Because the negatives attract the positives.
Okay, oxygen. You guys have started to draw what's called a Bohr diagram where you have different. You got your periodic tables. That's another thing you need to use, a periodic table. I can actually probably give you one that you can use. I have some here somewhere. There. It's in the front of it, right here.
I think I have an extra copy too. It's black and white.
Okay, that's great. They have one for you to use.
If you need one.
Okay. All right, you can use this one for now, too. I think that's the next one, so you can just keep that if you want. It's different than the one that they showed you, but, okay, what was the question we were talking about? Here's hydrogen. So, how many shells does hydrogen have? It's in row 1, which is called period 1, so it has 1 shell. All of these atoms, including oxygen, are in row 2, so they have 2 shells. Everything in row 3 has 3 shells. And that's all there is to it as far as your periodic table, you get the number of shells. So what happens is oxygen has a nucleus. What number is oxygen in your periodic table? What? It says 8. Underneath it you see 16.00. Most of them don't have numbers that come out exactly even. Like carbon is 12.01, etc. Why doesn't it come out exactly even? Anyone, what do you think?
Some, like isotopes.
They have different numbers of neutrons. You've heard of carbon 14-80. Carbon normally has 6 protons, 6 neutrons. 6 plus 6 is 12. Carbon 14 has 6 protons, 8 neutrons. That adds up to 14. On the average, because they have so few of the atoms are 14, nerds have 8 neutrons, that's just a little bit above 12, 4.01. Oxygen, there's some isotopes with only 7 neutrons, some with 9. It averages, just averages exactly 16. So the most common oxygen molecule has 8 protons and how many neutrons? 8. So it has 8 protons. So if you look at the shells around it, oxygen has 2 shells. In the inner shell, it's going to have 2 electrons. So we're going to pair them up like this. And I know you haven't talked about electron configuration yet, probably. Have you guys gotten into that yet? Yeah, but you will if you haven't, real soon, because it's something that most chemistry classes are doing now. Now what happens is the outer shell of oxygen looks like this. You're going to pair up those here s electrons, and you have 2 plus what adds up to 8?
6.
So I go electron, electron, electron. That's 5, so I need 1 more electron. You don't pair them up until you get every orbital has 1 electron. So you can see that this side could use, this got an opening right here, this has an opening here for another electron. So oxygen would like to get 2 more electrons. Hydrogen is real simple. There it is. It's got 1 shell, it's got 1 electron. It doesn't pull on this as strongly as oxygen, which has 8 protons in there, opposite charge attract, pulling on that electron they're trying to share. Because here's a hydrogen atom here, it's got electron they're trying to share to fill up their outer shell. Oxygen, because of the larger nucleus, attracts that electron more than hydrogen. So it basically, even though it's shared, have you got any brothers and siblings where you have something you share, but your sibling seems to share it most of the time, you don't share it as often. That's kind of what's happening here. Hydrogen doesn't get possession of the electron as often as oxygen. So that means oxygen tends to have those two extra electrons almost filled. That gives it a negative charge. Because hydrogen is kind of giving up that electron, that means it has a partial positive charge. So the upper part of this molecule is negative, the bottom part is positive. And electroconduction happens if you have electrolytes in the water. Anybody know what an electrolyte is? You have electrolytic drinks that you drink. What does it have in it if you read the bottle? Calcium, magnesium, you read stuff like that. Salts. Things which, when you put salt in water, it stays salt, but the sodium chloride, sodium has one electron in the outer shell, it just as soon get rid of. Chlorine is missing one electron, it just as soon take that electron. So when it breaks up, when it dissolves in water, what happens is this sodium develops a positive charge, the chlorine a negative. And this sodium gets surrounded by water molecules with the oxygen facing. Remember we saw a video on that last week, I think? Chlorine gets surrounded by water molecules with the positive hydrogen surrounding it. So they're both surrounded by water molecules. It's still salt. It still has properties of salt. So what happens is electricity can travel, electrons can travel from one antipositive to the next antipositive, and you can travel through it. So, did you guys ever see What Women Want? I think it was called with Mel Gibson, where he gets electrocuted because he's blow drying his hair and he's in the bathtub and he drops it. He tries to get out, he can't quite get out, and he gets electrocuted. When he comes to the next morning, he can read people's minds. He can hear what they're thinking. Nobody saw that? Well, it came out several years ago. But the point is, he dropped that hair dryer in the water. You don't want to do that, right? Because water doesn't conduct electricity real well, but it does conduct electricity. The more impurities you have, the more salts in the water, the better it's going to conduct electricity. So if you stir salt in a glass of water, you're going to find it conducts electricity a lot better than without it, because you added electrolytes. So that's what your lab is going to be about next week, is different solutions. Some conduct electricity better than others. You're going to try to figure out why some conduct electricity better. Now, what I want to look at is, we're going to look at a couple of videos. One is, what is a chemical equation? And then the other one is going to look at solutions with electrolytes and non-electrolytes. So, in a chemical equation, before we watch the video, it's a little bit like just a mathematical equation. And I know this is going to seem kind of overwhelming to you, and I would say it all at once. No time to get caught up. So, if we have an equal sign, we have a typical sign like that. So, like combustion is kind of the opposite of photosynthesis. Remember for biology, photosynthesis, you have carbon dioxide and water forming glucose plus oxygen. Do you remember that from last year in biology? The opposite direction. C6H12O6, that's glucose, plus oxygen with, when it combusts, is going to form carbon dioxide plus water. You will study in your books eventually different kinds of chemical reactions. Combustion always has some carbohydrate, oxygen on the left side, and it always forms carbon dioxide and water, always. Now, this is not balanced. How can we tell it's not balanced?
There's only 3 oxygen molecules in it.
Okay, you've tried to solve simultaneous equations, and you know you can multiply everything by a certain number, and you combine them so that you end up, solving it. Then you do a similar process here. 6 carbons here. How many carbons on the right side?
One.
Just 1. Okay. 12 hydrogens. We only have 2 here. Here's the way that you balance combustion equations. You start with carbon. And I'll put a 6 in front here because I need 6 carbons. Now, look at the hydrogen. What number do I need to put in H2O to get 12 hydrogens?
You're gonna put the 6 in front of the H.
You need, it turns out you need a 6 here also. Now, what's the total number of oxygen? 2. Each one of these carbon dioxide molecules has 2 oxygen atoms. 6 times 2 is,
12.
so there's 12 oxygen here. And how about this one?
That was just gonna be 6.
6 oxygen. So what's the total number of oxygen atoms on the right side?
18.
Okay. Now, we can't just put a 9 here, too, 9 is 18, because we already have 6 oxygens, don't we? So, how many more oxygens do we need on the left side?
12.
12. What number? 2 times what will give you 12?
6.
So it turns out for glucose, it's 6 is all that you need. Now, when you're done, check it out. 6 carbons, 6 carbons. 12 hydrogens, 12 hydrogens. 6 plus 12 is 18 oxygens. 2 times 6 is 12. 6, 18 oxygens on the right side. And it usually doesn't, it's just with glucose that happens, but for sucrose or something else it'd be different. So that's how you balance equations, is you usually with, I just look at combustion, you leave oxygen till last, you start with carbon. So that's one thing you're going to learn how to do. And let me get the video we're going to watch because I prepared them. It's not this. It's not the one. It's the first one. Is what is a chemical equation and definition examples. I have a little PowerPoint that's linked to it online. It's only 6 slides. It's really basic. Can you turn off the middle switch back there? Get this on here. So what you want to do is you do want to do the quiz, etc. afterwards. By the way, I want to point.
A chemical equation is a shorthand way to.
Let me stop before they go on. I have notes here somewhere. Yes. Every one of the videos that we watched, like we watched a video on the scientific method, on chemical lab safety, and the metric system. And then chromatography and forensic science. We watched those. The chromatography and forensic science, that quiz needs to be done. Some of you have already done some of them. It is due by the 17th. But those other 3, scientific method, chemical lab safety, and the metric system, you need to do when you watch the video online and after there's a quiz, you can take the quiz as many times you want to, you get 100%. And that's due by next week. It says by the 10th, which is Friday. I don't know why, but that is what it says. So, of course, you have more time. Don't worry about it. Yes?
Will the test next week be based on the videos?
Well, sure. Yes.
Not the labs?
The quiz, no, it's the labs, but the videos are helping explain the labs, so yes.
Okay, so.
I think the quiz is a good way to anticipate what you need to know, right?
Okay.
But some of the things that you need to know, let's see. Okay. You need to know what chromatography is, about the scientific method. You need to be able to convert. Let's say if I gave you so many milliliters, convert it to liters, so many liters, convert it to milliliters. Same thing with centimeters to meters. Be able to do conversion. And then they're going to ask questions about what we're going to watch now, chemical equations. So why don't we let it play, and then we'll see what questions you have.
To represent the components of a chemical reaction, there are several pieces of information provided in a chemical equation for those working with a chemical equation or corresponding chemical reaction. You've worked with equations in mathematics, where an equation is used to represent information such as equalities or inequalities. Chemical equations are different from mathematical equations because the 2 parts of a chemical reaction represent the before and after of a chemical reaction. In mathematical equations, an equal sign separates the 2 parts of the equation. In chemical equations, equal signs are not used. Instead, an arrow is used to separate the 2 sides of the equation, and it points in the direction that a chemical reaction will proceed. To make a large glass of lemonade, use 1½ cups of water plus ½ cup of lemon juice plus ¼ cup of sugar. Here's a recipe for the formation of water from molecular hydrogen and molecular oxygen. 1 mole of oxygen plus 2 moles of hydrogen yields 2 moles of water. Note that just as a cup is a quantity in a recipe, a mole is a quantity in chemical reactions. To write the equation using the chemical symbols and components of a chemical equation, we would write O2 plus 2H2 yields 2H2O.
Okay, do you guys know what a mole is in your different classes? I know you've already, anybody else know what a mole is?
It's like a unit.
It's what?
It's like a unit.
Okay, it's a unit of measurement. Have you talked about Avogadro's number in your books?
Yes.
Know what it is?
I don't remember off the top of my head, but I remember hearing it.
6.02 times 10 to the 23rd. It turns out, if you have 6.02 times 10 to the 23rd hydrogen atoms, they will weigh 1 gram. If you look on the periodic table, you can see hydrogen, what's underneath 8 is 1.008. That's how many grams 1 mole. 6.02 times 10 to the 23rd is a number. We call that Avogadro's number or a mole. A mole is that many of it. So if you look at oxygen, you see underneath the O 16.00. Now, oxygen usually comes as O2. So each one of those, you know, is 16.00. So what you have is a total of 32.00. So if you have 1 mole of oxygen, it will weigh 32 grams. That's the neat thing about a mole. You can use the atomic mass on these to determine their mass if you have a mole. If you have, let's say you had some solution that was 1/10 molar, that means you have a tenth of a mole. So instead of being 32 grams of oxygen, it would be 3.2 grams because it's a tenth of a mole. You know, that's, so they make solutions where they dissolve things in a liter of water, and if you have 1 mole dissolved in 1 liter of water, it's called 1 molar. If you had a weaker solution of it, it might be 0.2 molar. That's going to be 1/5 as much. So anyway, that's, if you haven't, before the test, I would look up the idea of mole, make sure you understand what that is. It's just a number, and it's designed to work with the periodic table to make calculations much easier. So we'll let them go on now.
As you can see, both the chemical equation and the recipe for lemonade provide adequate information that shows how to create a new product. In general, we represent an equation in this way. A plus B yields AB reactants yield products. We say that there are left and right sides of an equation and that they are separated by an arrow. The arrow can be a right-pointing arrow, a left-pointing arrow, or a double-headed arrow, depending on the chemical species and equilibrium involved in a chemical reaction. You can read the arrow as goes to, forms, or yields. To represent a generic chemical equation, we often use alphabetic letters. We read the equation as A plus B yields AB, or A plus B forms AB, or A plus B goes to AB. Note that A and B are reactants, and AB is the product, a newly formed substance in a chemical reaction. There are many different kinds of chemical reactions, and they vary in the number of reactants and products. The diagram shows the schematic of the variety of ways reactants and products can change or rearrange in a chemical reaction. Because a chemical equation represents a chemical reaction, it's important to understand what a chemical reaction is. You observe chemical reactions taking place every day. A chemical reaction occurs when matter is rearranged to form a different or new substance. Fry an egg, or cook anything really, and a chemical change takes place. The beautiful night sky on the 4th of July is an amazing display of chemical reactions taking place. Burning a log in a campfire is an example of a combustion chemical reaction. Even that old rusty screw on the floor of your garage is the result of a chemical reaction having taken place. We say that a chemical change has taken place in a chemical reaction. To help us understand how the matter was rearranged, we use chemical equations to symbolize what chemical changes have taken place. As you've learned, the main parts of a chemical equation are the reactants and the products. information provided in chemical reactions involves the number of atoms and molecules in a chemical reaction, shown with coefficients and subscripts. A number in front of a reactant or product is a coefficient and indicates the number of the species required for the chemical reaction to occur. Chemical equations must be balanced, meaning that the same number of atoms entering into a chemical reaction must come out of the chemical reaction. It is the coefficient placed in front of the reactants and products that balance the chemical components of an equation, and you will learn how to balance chemical equations using coefficients in another lesson. In the following equation, note that there is a 3 in front of molecular hydrogen and a 2 in front of ammonia. When the coefficient of a chemical species is 1, as is the case with N2, it is not written in the equation, but
Just like
looks
an
like to be
algebra.
1. A subscripted number is the number of atoms in a particular chemical species. For example, in this chemical equation, the subscripted 2 indicates that 2 atoms of hydrogen make up molecular hydrogen, and there is 1 atom of nitrogen and 3 atoms of hydrogen in ammonia. Some chemical reactions need a substance to speed up or catalyze a chemical reaction. Examples of catalysts are heat, electricity, and certain chemicals or metals, such as platinum. In a chemical equation, the requirement for a catalyst in a chemical reaction is written above the arrow. Often, it's important to know the physical state of a reactant or product. These physical states are represented as follows. For a gas, G is shown. A solid is indicated with X, a liquid with an L, and an aqueous solution by AQ. The abbreviations for the physical states of the chemical.
Aqueous solution just means that you have something dissolved. You should dissolve salt in water. So if you were to write NaCl, you put in parentheses after aqueous, means it's dissolved in it.
Components in an equation are always italicized. This diagram summarizes the components in a chemical equation. You'll want to become familiar with the information provided in a chemical equation and relate it as a recipe for making new chemical substances.
Summary.
We learned that a chemical equation is used to show how products form from reactants. You learned that the reactants are always on the left side of a chemical equation, and that the products are always on the right side of the chemical reaction, and that a chemical equation is analogous to a recipe. We also learned that the number of atoms and molecules undergoing a chemical reaction, the physical states of the reactants and products, as well as whether a catalyst is required in the chemical reaction, is all information provided in a chemical equation. As you continue in your study of chemistry, you'll be exposed to many different chemical reactions and their corresponding chemical equations. You'll become an expert in interpreting these because you now have an understanding of the components of chemical equations and how they're represented.
Okay. So just as, think about it. You look at this, this says you have nitrogen gas and hydrogen gas, they react to form this. What has to happen is you have to break the bonds between these two nitrogen atoms, break the bonds between these hydrogen atoms, and then you have to collide in such a way that you form new bonds. And that's why, if we look at the amount of energy, you know, over time, what's happening, you'll see start in this state. You do something like this distance right here is called the activation energy. Remember we talked about that before? That's the energy needed to break those bonds. Now, when they form new molecules, they may really be much more stable as ammonia now, and it may give off more energy when it forms new bonds than you had to put in to break these bonds. It takes energy to break them. And if it forms more energy, it might end up right here. Here's your products. And your reactants are right here. That's what we start with. So, you can see this is the amount of energy to break the bonds, this amount of energy released when you form the new products. So if it takes so much energy, but then it gives off more energy once you get it started, that's called exothermic. It's giving off heat. So I take a little mask and I light it to a piece of paper. It takes a little bit of heat, energy to get that paper start burning. But once you get it started, it's giving off a lot more heat than what you put into it, right? So it's exothermic. But this could happen instead. You could have it go like this, and here's your products out here. And if that happens, it's called endothermic, when there's less energy given off when you form the new compounds than energy needed to break them originally. Okay? And you guys already learned that, if we just look at the green one here now, if you use a catalyst, what a catalyst does, it requires less activation energy to break the bonds. It's something that goes into the reaction, a catalyst, causes it to break up, and then it forms the same new products, and it comes back out of it. And so the catalyst never gets used up. It just enters into it, but then comes back out of it again. So this is a review on that. And by the way, to balance this, I could start with any one, but let's start with the nitrogen, because there's an odd number of hydrogen. We have 2 here, so what do I need to put in front of this to get 2 nitrogen over here?
I have to put a 2 in front of that
2
one.
in front of this one. How many hydrogens do we now have on the right side?
6, you have to add 3 to the hydrogen.
So that's it, put a 3 here. This one is understood, you have to write it. And that's how, it's not difficult to balance them. Some can be really hard to balance. And yeah, that's second semester ones that are hard. So let's look at the second video. Let's see, solutions, electrolytes, and non-electrolytes.
Most things in your daily life.
Sorry, I did want to say something. So remember, these are your reactants, these are your products. And make sure that, as they pointed out in the video, the number of atoms on both sides are the same. So the left side we have 2 nitrogen and 6 hydrogen. The right side we also have 2 nitrogen and 6 hydrogen. Yes?
When we write out the equations, do you want us to put a 1 in front of the nitrogen? Like, your
No,
example?
no, I'm just doing it to make sure it's clear.
Okay,
You know,
just want to make sure.
if you had x plus 2y equals 6 for some, equation, linear
Right.
equation, you wouldn't put a 1 in front of the x, right?
Yeah, I never put
Same
the 1 in
idea.
front when I did it at home. I just didn't know if you prefer.
Right, no, don't put a 1 in front. If it helps you, just make sure that this is kind of for understanding, but you don't. All right, so now we're going to look at electrolytes and non-electrolytes.
Mixtures. Milk is a mixture. Shampoo is a mixture. Air is a mixture. A mixture is 2 or more substances that are mixed but are not chemically combined. There are 2 different kinds of mixtures, heterogeneous and homogeneous. In a heterogeneous mixture, like salsa or chicken noodle soup, the different substances are distinguishable from one another. In homogeneous mixtures, the different substances inside are indistinguishable from one another. The physical properties of a homogeneous mixture, like air or Gatorade, are uniform. Solutions are homogeneous mixtures made of a solute and a solvent. Solutes are substances that get dissolved. Solvents are the substances that do dissolving. Solutions can be made up of any 2 phases of matter. Solutions may be made up of gases dissolved in gases, or solids dissolved in liquids, or liquids dissolved in liquids. Most of the time, solutions are made up of a solid solute and a liquid solvent.
If you have a liquid dissolved in a liquid, how do you determine which one's called the solvent and which one's the solute? Because you do have that.
Whichever one's smaller, so.
Yes, whichever one is smaller is a solute, whichever one you have more of is the solvent. So if you have water and you have rubbing alcohol mixed in, you have greater bond with water than you do rubbing alcohol. Water is the solvent, the rubbing alcohol is the solute.
Water is often referred to as a universal solvent because it is capable of dissolving so many different substances. In this lesson, we will be looking at examples of solutions made of solid solutes and water as the solvent. One of the most important qualities of a solution is its concentration. A solution isn't chemically combined, so it can have different amounts of solute dissolved in the solvent.
Very important.
More solute or solvent means a more concentrated solution. Similarly, less solute or solvent means a less concentrated solution. The concentration of a solution is most frequently described in terms of molarity. Molarity is the number of moles of a solute per liter of solution. It has the
Okay, I know you haven't really covered this yet, most of you haven't, but what they said is molarity, which is a capital M. One, molarity has to do with the number of moles of some substance per liter of water, called molarity. So if you take glucose and you want to dissolve it, that's not a good example because it's a lot of glue. Sodium chloride, you want to dissolve it in water. On your periodic table, what do you see underneath sodium for the atomic mass?
22.99.
22.99. What do you see underneath chlorine?
35.45, 30.
35 point what?
45.
Okay. You have one of each. So if you add those up, let's see if I do this right, I think it's 58.44. Okay? So if you have 1 mole of this, it's going to weigh 58.44 grams. So if they say to make a 1 molar solution, you're going to take 58.44 grams of table salt and dissolve it in 1 liter of water, and that is 1 molar. If they said we need it to be 0.5 molar, you're going to take half this amount, dissolve it in a liter of water. That's what molarity is about. It's a way to describe how concentrated a solution is. Remember, a solution is just a mixture. It's not a chemical reaction. When you put salt in water, drink it right, does it still taste salty?
Not quite the same.
But it still tastes salty, right?
Yeah.
Meaning it hasn't been a chemical reaction. That sodium chloride is still there in the water, because you can tell it wasn't because a chemical reaction would taste different completely. So, anyway.
Lowercase n. Molality is useful when performing calculations involving the boiling or freezing points of solutions. Lastly, solution concentration can be described by mass percent, which is the percent by mass of the solute.
The last two isn't used very often in
Mass
chemistry.
percent can be calculated by dividing the mass of the solute by mass of solution and multiplying the result by 100%. Mass percent is often used in analysis of solutions, like water quality reports. Imagine you work for a chemical supply company, and for every solution you make, you must give a report on concentration in terms of molarity, molality, and mass percent. Today, you have to dissolve 85.58 grams of sucrose, table sugar, in 1.5 liters of water. The molar mass of sucrose is 342.3 grams per mole.
You do that by a C12H42O11. So you go, carbon is 12.01 times 12. Take hydrogen, is 1, 22 times 1. Oxygen is 16 times, 11. And you add them all up, and that's the number you get. That's how many grams per mole.
The first task on my list is to calculate molarity for the solution using the molarity equation. Molarity equals moles of solute divided by liters of solution. We have liters of solution given to us, but must calculate number of moles given both the mass of sucrose and the molar mass of sucrose. To find moles of sucrose, we divide the given mass of sucrose by the molar mass of sucrose. 85.58 grams of sucrose times 1 mole over 342.3 grams of sucrose. This equals 0.25 grams of sucrose. Now, we divide our number of moles solute by our liters of solvent to find molarity. 0.25 moles sucrose divided by 1.5 liters of water equals 0.17 moles per liter. Or, we have a 0.17 molar solution. Our next task is to find molality using our molality equation. Molality equals moles per solute over kilograms of solvent. We know that we have 0.25 moles of solute, which we just figured out in our previous problem, and 1.5 liters of solvent. We must convert liter solvent to kilogram solvent. The density of water is 1 kilogram
So it makes
per
it
liter,
easy.
meaning that the mass of 1 kilogram of water is equal to 1 liter. We have 1.5 liters of water equal to 1.5 kilograms of water.
11:40 is when our class ends.
Oh, good, what am I thinking? This class started at what time?
10:30.
10:30.
It's 7 minutes.
So, 10:30, of course, great, never mind.
In
Good.
1880, Swedish chemist Svante Arrhenius recognized that some solutions could conduct electricity. He noted that the number of dissolved ions in solution is directly related to the strength of the solution's electrical potential. Compounds that dissolve by breaking into ions and conduct electricity in solution are known as electrolytes. Most soluble salts, acids, and bases are electrolytes. Compounds that dissolve in water but do not conduct electricity are known as non-electrolytes. Non-electrolytes are often covalently bonded compounds like sugars or alcohols. Not all electrolytes have the same strength. Electrolytes that are strong conductors of electricity are known as strong electrolytes. Examples of strong electrolytes include sodium chloride, hydrochloric acid, and sodium hydroxide. Other electrolytes that conduct electricity poorly are known as weak electrolytes. Substances such as acetic acid, citric acid, or ammonia are weak electrolytes. As mentioned in the electrolyte segment, compounds that produce ions in solution are the best electrolytes. Compounds that contain ions are ionic compounds. Ionic compounds are neutrally charged compounds made of a positive metal ion bonded by electrostatic attraction to a negative nonmetal ion. Many ionic compounds can be dissolved in water. These ionic compounds are strong electrolytes. Other ionic compounds dissolve poorly in water. These ionic compounds are weak electrolytes. It's hard to predict whether or not an ionic compound will be a strong or weak electrolyte without a little help. This solubility rules table is designed to help determine if an ionic compound will dissolve in water or not. The first column shows an ion or group of ions. The second column indicates the general solubility of those ions. And the third column lists any exceptions to the general solubility of the ions in the first column. For example, all group 1 elements are soluble, no exceptions. Chlorides are usually soluble except when in the form of silver chloride, HECl, mercury 2 chloride, Hg2Cl2, or lead 2 chloride. Non-electrolytes are usually covalent compounds, which are formed when 2 or more nonmetals bond together by the sharing of electrons. While some of these compounds, like sugar, may dissolve well in water, they usually don't dissociate to produce ions. Some covalent compounds, like the weak electrolyte ammonia, may cause other compounds to form ions, but ammonia itself does not dissociate. A mixture is when 2 or more substances occupy the same space, but are not chemically combined. A solution is a homogeneous mixture of 2 or more substances. One of the most important properties of a solution is its concentration. Concentration may be expressed in terms of molarity. Molarity equals moles of solute per liter solution. Molality. Molality equals moles of solute per kilogram of solution. Or mass percent. Mass percent equals mass solute divided by mass of solution times 100%. Electrolytes are substances that dissolve by breaking into ions in solution and conduct electricity. Electrolyte solutions can conduct electricity. Solutions that dissolve in water and don't conduct electricity are non-electrolytes. Ionic compounds are generally electrolytes. Covalent compounds are generally non-electrolytes.
Okay. That was good for now. So I know that's a lot of material, and some of you guys haven't covered this yet. But on the quizzing for the first 3 labs, actually it's going to cover the first 3 labs. Though next week is when we do lab 3. So you need to read up about it in your book, about what we're doing. So this lab next week we're doing is covering electroconductivity. If you have more electrolytes in a solution, it'll conduct electricity better than if you don't. So that's kind of obvious. Another thing you'll get is, let's say, let's pick carbon, that's a real common element. And the 6 will either be up here or in the corner, I'll put it straight up here. Underneath it, it says 12.01. What this technically is saying, that there are 6 protons, and it always has the same number of protons as electrons, unless it's 9, so that means 6 electrons also. This is the size of the nucleus and the average. That assumes protons and neutrons are the same size, because they're not exactly, but they're very close. But they are different slightly. So that's the total mass of the nucleus, which would say on the average you have 6 protons and 6 neutrons to make 12. So that's the kind of thing you'll be checking to see if you understand. Underneath it, it'll say here carbon, the name of it. So that's the symbol. So this is the atomic, what do you call it, guys? Atomic what?
Atomic number.
Number, which is the number of protons and electrons. If it's carbon, it always has 6 protons in the nucleus, always. The number of neutrons can change, but it always has 6 protons. If it's oxygen, it always has 8 protons. It's atomic number 8. This is called what? Atomic what?
Atomic mass.
Atomic mass, sometimes referred to as atomic weight. And that's the size of the nucleus. And this is the name of the compound, and that's atomic mass. That's basically all there is to it. If they give you something like this carbon, which has 6 protons, and let's say its atomic mass is 14, how many neutrons would you say it has?
8,
And how did you come up with that?
14 times
Right. So we know that this is number of protons plus neutrons. This is number of protons. So 6 plus what is going to add up to 14. You can tell it's 8. That's all there is to it. It's not hard to determine that. So when they say something like carbon 14 or carbon 12, the 14 is atomic mass. They don't have to tell you the atomic number because they figure, you know, if it's carbon, the atomic number is 6, or else it's not carbon. So anyway, that's some of the things they'll expect you to know how to do. Need to know what electrolytes are and non-electrolytes. Both sodium chloride and you could say table sugar, which is C12H22O11. I'm not going to memorize that right now. When this goes in the water, what happens is you get a sodium atom here, so and a chlorine atom. It's still it's not a chemical reaction, but each one of these is surrounded by a water molecule. Here's the hydrogen, and that's oxygen. This is the negative charge, and this is the positive charge. So the oxygen atom is surrounded by all these water molecules like this. The oxygen is going to be closer to the sodium because opposite charges attract. The sodium has a positive charge, so it's surrounded like that. Chlorine is surrounded, but it looks like this. Why do you think it looks different? Anyone, what do you think?
Because the chlorine is negative.
Because the chlorine's negative, and so the positive side of this polar molecule is hydrogen, and that's going to be closer to the chlorine. So that's what happens when things dissolve in water. These are electrolytes. Sodium chloride is an electrolyte because it breaks down into ions. And it's basically what an electrolyte is. They break down into ions and they will conduct electricity. Some are stronger electrolytes than others. This is a non-electrolyte because it dissolves in water, but it does not break down into ions. So it's not adding sugar to water, you're going to find will change how much electricity is conducted by the water. Whereas adding salt will make a difference. That's what you'll see in the lab this week.
Do we have a lab due this week?
Let's see. Check the last one and see what we had. No. None due this week.
We took a lab report, or we had a lab last week.
Yeah, so I thought the
And
report was
we're
due
report, greater assignment is due this week, let's note it. Report for lab 2 melting point, yes, we do. Report for melting point. Did that work for you guys pretty well? Did you see the difference? At melting, they're just supposed to melt at a certain temperature, but. Pardon? Good. Okay.
Wait, was this as long? Mine is not long, I just wrote all the steps out from the manual.
That's
So-
serious.
And then I just copied it word for word from the manual.
Well, honestly, her math doesn't let you read it.
I quoted it though.
Can I get your lab reports from the rest of you guys?
I'm gonna run back.
Okay, thank you.
Three people.
Okay.
Yep, that's one.
Okay, so in lab reports, you're going to learn that we always have, in the introduction, you have an hypothesis, and you always express it as if, then. If I do this in the lab, then I expect this to happen, or not, or whatever. So that's how you're going to express your hypothesis. Let's see, what else do we have there? Nothing.
And we just studied for the quiz last week, so.
Yes.
Yeah.
Woo, we're studying.
Wait, what is our test?
We're not. Yes, is next week, right?
Yeah,
It's a test or quiz?
quiz.
It's quiz, yeah. Okay, let me pull up one more thing, and that's the PowerPoint chemical equations. Okay, this is. It's coming up, it pops it up, there we go. Now, the reacting sodium and chlorine gas produces sodium chloride, which is common table salt. Now you know it's a chemical reaction because sodium is a highly reactive metal that in water it explosively reacts. Chlorine, as you see, CO2 is gas. It's one of the most poisonous gases around. You combine them together and you get table salt. Completely different than the sodium and chlorine, so that's a chemical reaction. If something is dissolved in water, it's not a chemical reaction, they're just mixed together. So, what we call the left side, the sodium and the chlorine. And guys, you need to start looking at your periodic table, become familiar with the names. Most books in the front of it will have periodic table, and then maybe the next page will have a list of all the elements, their symbol and their names. So you want to become familiar with them, especially the first about 50 or so elements. That's a good idea. So what do we call this left side? Reactants, because they're going to react. And the right side? The product. This is just one product. Okay. And you see, you had Na plus CO2 goes to NaCl. We saw that if you just put, and you didn't have the 2 here, we would see that we need 2 chlorine. So you put a 2 over here so that you got 2 chlorine. But that says, oh, I need 2 sodium. So you came back over here and put a 2 in front of this. That's all there is to balancing them. They're not that hard. Okay, now, this says 2 sodium atoms, 2 molecules of sodium chloride, and you'll learn down the road how to name compounds. And then this one says there's 2 chlorine atoms bonded together to form a chlorine molecule. Those are reactants, and that's the product. See how that works? Now, same thing with this. You have magnesium and oxygen for magnesium oxide. How many atoms of magnesium react with 1 molecule of oxygen?
Sorry, City.
Pardon?
City.
How many atoms of magnesium react with 1 molecule of oxygen?
2.
2. Okay. And it forms how many molecules of magnesium oxide?
2.
Yes, it does. Okay. So reactants, products, 2 magnesium atoms, 1, okay, 1, that's wrong, 1 oxygen molecule. with 2 oxygen atoms in it. Okay, we'll go back. So again, this should say 1 oxygen molecule, not atom. And the 2 there says each molecule has 2 oxygen atoms. So we've got 2 oxygen atoms bonded together. If you have 2 oxygen atoms, because you have a lot of gases that are like this, what are they called? H2, O2, N2? What are those things called? What kind of molecule is that? What do you use to indicate 2 often? Mono means 1. What do you use for 2?
Oh, like di.
Pardon?
Di.
Di. Okay. They're called a diatomic molecule. Diatom. 2 atoms. Any molecule that just has 2 atoms of that stuff is called diatomic. Just if I cover that in books. So that first molecule, CH4, is called methane. And then you have oxygen, and you can see carbon dioxide and water. This is an example of combustion. Just a reminder how to balance that. It's not hard. It's not very long PowerPoint here. So we started out with CH4 plus oxygen. You see oxygen on the left side with a carbohydrate? That's combustion. It always forms carbon dioxide plus water. Combustion always forms carbon dioxide plus water. Let's see how to balance that. You can already see what it is. Leave oxygen to last. 1 carbon, 1 carbon, not a problem. 4 hydrogen, 2 hydrogens. What do I need to do to make 4 hydrogens on the right side?
Add a 2 to the front of the H.
Okay, now we have 1 carbon, we have 4 hydrogen. The only thing not balanced is oxygen, which you always need to last. Sometimes this first one here will have oxygen in it, but in this case it doesn't. So how many total oxygens do we have here?
4.
2 plus 2. There are 4 oxygen atoms. So what number needs to go in front here?
2.
And does that look like what they have there?
Yeah.
So they're pretty easy. The oxidation ones, they look messy, but they're really easy to balance. So 1 molecule of ammonia reacts with how many molecules of oxygen?
2.
And how many, pardon? On the left side, 2. And how many total atoms of oxygen are there on that left side?
4.
Because you have 2 molecules of oxygen, diatomic, and so that's 2 and 2, it's 4. Okay, and again, that's the reactants, and this is the products, and that's called carbon dioxide, meaning 2 oxygens. And this is water, or dihydrogen monoxide is what water should be called. You'll learn about that in your class, how to name these things.
Let's
This-
stick with water.
This part, it's also called carbon tetrahydride, but it's just methane, just like this is just water. And this is just oxygen. Okay, so now let's look at this one. Balancing this would have been fun, but
Oh.
you have 6 nitrogen atoms, and only how many molecules of aluminum oxide?
2. Wait, no, there's only 1.
Just 1. There's no coefficient in front, so it's 1. And how many molecules of sodium oxide is formed? 3. And how many atoms of aluminum?
2.
Okay. This is called single replacement. Because what happens is nitrogen replaces aluminum to bond with oxygen. It says, get out of there, bully, and I'm stronger than you are, I'm going to kick you out, and I'm going to take over oxygen. So what's left out here by itself now? See, here was sodium by itself, and now here's aluminum by itself. It's called single replacement. Sometimes they exchange places. And so, when you do that, again, you usually want to leave with oxygen to last, but we'll talk about balancing later. But again, recognize what you see here. You see the number 6 sodium atoms on the left, and how many are on the right? Well, 3 times 2 is 6. Since each one of the sodium oxide molecules has 2 sodium atoms, 2 times 3 is 6. The aluminum atoms, 2 aluminum on the left and 2 on the right. How about the oxygen? Well, I'll go back. How about the oxygen?
There's
We
3.
have 3 3 here and 3 times 1, 3 there. So you can tell that the number of each all balances. So it's all right. So that's another kind of reaction. And again, going back to this, what you need is you need so much energy to get these bonds to break, and then when this sodium jumps in and combines with oxygen, you have energy released. The energy to get it to break is called activation energy. The energy given off when it happens is determines whether it's going to be exothermic or endothermic. Exo meaning out, endo meaning in. So since in this reaction more energy is given off than is needed to break it, it is exothermic. So anyway, enough on that. So, do the worksheet and take the quiz. So any videos you watched in class, you look for the last few weeks that you've done, remember by the 10th, we want you guys to have done that for the scientific method video, chemistry lab safety video, and the metric system video. The chromatography and forensic science we watched last week, I think it was last week or maybe the week before, that's not due till the 17th, I believe. Yeah, I think that one's due the 17th. So just a reminder. And we have till 11:40 or 11:45?
11:40.
We got 5 minutes, good. Okay. Don't do that anymore, because I want to show the attendance. Okay, good. Let's go to communicate, teacher pages. So, just a reminder, let's see, what is chromatography definition, types and uses, chromatography and fluorescent science, we'll do the paper chromatography experiments. Let's see, we did the lab, and then this is a link, let's see, yeah, for the periodic table, which you guys have printed out. I think it's black and white. And that's fine, the periodic table they suggest to use. Yeah. So anyway, all the videos that are at study.com that you're supposed to watch, I think we all watched in class, but remember you need to go back and make sure you completed taking the quiz. You can take the quiz, I believe, as many times as you want.
Yeah.
And so bring it, why not bring it up to 100%? No reason why not. So, student assignment says, watch the following videos if you haven't done it yet. What is the chemical equation, solutions, electrolytes and non-electrolytes, and atomic number and atomic mass? Reread lab 3 because the quiz next week is going to cover everything we've done in the first 3 labs, even though we haven't done that yet. So, there's PowerPoint presentations, materials on GradeLink, and your lab manual, and that should be a good preparation. And due this week, you already turned in about 2 minutes. Okay. Well, you have any questions? I'm done with what I wanted to cover. Are you feeling overwhelmed?
A little bit.
If you're a good student, it won't be a problem. Just take your time to get caught up, and we'll figure it out. You go. The lab, do you have a lab manual? Do you have one of these?
I think I'm ordered one.
Okay.
I can take pictures of mine if you'd like. Just
Pardon?
like that's true.
Okay.
Unless there's here, there.
Okay. I've got this one. When it arrives, what your mom's ordered, you can just return it.
Okay, thank you.
So you have something to far as liquid. It's got good material in there, and remember, your quizzes and tests are based on what we covered in the lab. So you may not have covered something yet in your book, or you may have covered it a while ago, but what we're covering, with the quiz you want to assume you know something. So they expect you now pretty soon. I don't think you're going to be quizzed on that yet. No, you're not going to quiz on it yet, but pretty soon they want you to know about molarity. Remember, it's moles per liter, and that's how concentrated a solution is. And the way they did it is an exact reference, pretty close. If you start with, if you're going to dissolve sodium chloride, we already said it's 58.4 grams per mole. You look that up by adding up, we did this earlier. So let's say you had 85 grams of sodium chloride, and you're going to dissolve it in 1.5 liters, like they said. So you're going to start with this, and then you're going to multiply that by 58.4 grams of sodium chloride per 1 mole of sodium chloride. So then the grams of sodium chloride cancels. So now you got moles of sodium chloride. And now what we're really going to do is we're going to put this 85 grams per 1.5 liters. Because that's what you did. You dissolve 85 grams in 1.5 liters times. And then when you're done with that, you're going to get 85 times 1 divided by 1. You're going to get the molarity. And they use a capital M for molarity, whatever that comes out to be. But practice using dimensional analysis. Some questions about using dimensional analysis to convert from grams to kilograms or milliliters to liters. Or when we get into the solutions, I have handouts I use in my other class. I think I have them if I can give it to you guys. That explains how to work with moles. First, it's called stoichiometry. So if you look in your books where stoichiometry is, it sounds kind of hard at first, but actually once you get the hang of working with molarity, it's not that hard. It's kind of fun. I think it's fun. Again,
Fun for people who means different things.
yeah.
Let's say it like that.
Okay, Benjamin. Pardon? Yeah, I think you were here when that these up. Yes. That's what you do. Frankly, if I bring it up, you know how you can bring it up the next week. Make it worth it. All right, see you guys next week. We'll do this lab and be ready for your quiz. We'll do the quiz first.
Okay.
So do preview the lab because it's going to be stuff first to be covered in the quiz.
Okay. Thank you.
Yep, not Kaylin, but the rest of you. Thank you. Kaylin?